If you're driving a modern dual-motor electric vehicle down a highway at like 70 miles per hour, there's this tiny piece of plastic film sitting directly under your seat.
Yeah, right under you.
Right, and it's roughly the thickness of a human hair.
Basically microscopic, yeah.
Exactly. And at any given moment, that microscopic layer of plastic is really the only thing standing between your car operating perfectly and, well, a catastrophic high-voltage explosion.
It is the single point of failure.
So today we're doing a deep dive into this highly classified stack of engineering specifications to look at exactly what happens when that plastic starts to die, and how the vehicle's brain fights to keep it alive.
Right, we're looking at a very specific and incredibly critical failure mode from the functional safety architecture of hybrid dual-motor power control subsystems.
A mouthful, I know.
Yeah, it is. But in the engineering world, this is actually logged under the inverter and power stage category as fault B06, so DC link ripple anomalies.
Which sounds like, I don't know, something out of a theoretical physics paper.
It really does.
But the documents we have today, they detail the life cycle of this failure with absolute precision. I mean, we are tracing the journey of a failing component all the way from the microscopic physics of its breakdown, through the software algorithms that sense it dying, down to the structural blueprints meant to protect it, and then into the literal torture chambers engineers use to validate the whole thing.
The stakes here are absolute, because the DC link capacitor is the critical buffer.
Right.
It basically sits between the vehicle's massive direct current battery and the alternating current that's demanded by the motors. It acts as an electrical shock absorber.
And if that shock absorber fails,
the entire propulsion system halts, just instantly. And what these documents reveal is that this component rarely fails cleanly. It doesn't just snap in half.
right, it's not like a broken axle.
Exactly. It suffers from this invisible compounding disease.
And that decay is where we really need to start. Because before we dive into the incredible countermeasures the car uses, we have to understand the physics of the breakdown itself.
Right, the root cause.
Yeah, the root cause analysis in these specs points to 4 distinct mechanisms of failure. And the first one is actually built into the chemistry of the component itself.
Yeah, the degradation of the film capacitor.
Right. We're dealing with metallized polypropylene film capacitors operating in a brutal environment. I mean, they're experiencing temperature swings from -40 up to 105 degrees Celsius.
Which is extreme. And when you combine those thermal swings with intense high-frequency ripple currents...
Wait, explain ripple currents real quick for the listeners.
Sure. So ripple current is basically the electrical turbulence caused by the inverters rapidly chopping the power thousands of times a second to feed the motors.
Oh, okay. So it's not a smooth flow.
Not at all. It's violent.
Yeah.
So under that combined thermal and electrical stress, the plastic dielectric film experiences these localized microscopic electrical breakdowns.
Like tiny lightning strikes.
Exactly. Tiny short circuits sparking deep inside the layers of the capacitor.
And I want to focus on how the capacitor handles those microscopic shorts, because the mechanism here is absolutely fascinating. The component is designed to be self-healing.
Right, self-healing, but not in a biological way.
No, it's not like repairing tissue. It's more like a microscopic fuse. When that tiny short circuit occurs, it generates an instantaneous spike of intense heat.
Right, a massive localized thermal event.
And that heat literally vaporizes the incredibly thin aluminum metal layer surrounding the puncture.
It just flashes into a gas.
Yeah, flashes into a gas, which leaves this barren ring of unmetallized plastic around the short, completely isolating the fault.
So it's isolating the damage to prevent a catastrophic failure of the whole unit.
So it's like a sci-fi ship sealing off a breached hull section to survive.
Oh, I like that analogy.
Right. It lives to fight another day, but the ship gets smaller and less efficient every time it happens, which eventually leads to a critical failure.
That's a perfect way to look at it. The immediate crisis is averted, the capacitor survives, but there's a massive hidden cost.
The compounding disease you mentioned.
Exactly. Every time a section of that metal layer vaporizes, the capacitor loses a fraction of its active surface area. And in electronics, surface area directly dictates capacitance.
The actual ability of the component to store energy.
Right. So over thousands of these microscopic self-healing events, the total capacitance continuously drops.
And the damage doesn't stop there, right? Because all that vaporized metal doesn't just disappear into a different dimension.
No, it doesn't. It creates carbonized byproducts and degrades the internal structure, which means the equivalent series resistance, or ESR, begins to spike.
Wait, so it's the double whammy. The component is simultaneously losing its ability to buffer energy while becoming more resistant to the flow of current.
And the mathematics of this decay are just punishing, because the voltage ripple amplitude across that capacitor is inversely proportional to its capacitance
Okay.
and directly proportional to its resistance. So if your capacitance is decaying while your resistance is climbing, the voltage ripples don't just increase linearly.
They explode.
Right, they grow exponentially. The system is pushed into a runaway thermal and electrical spiral.
Wow. Okay, so that covers the chemical breakdown.
Mm-hmm.
But the second root cause in our stack shifts us from material science to, well, software timing.
Carrier desynchronization.
Right. We have two independent motors, motor A and motor B, pulling massive amounts of power from this single shared capacitor.
And to manage that electrical stress, the system architecture runs the switching frequencies of those two motors exactly 180 degrees out of phase.
So they're perfectly offset.
Right. When motor A is hitting its peak electrical draw, motor B is at its valley.
So the electrical ripples crash into each other and actually cancel each other out.
Exactly. Destructive interference. It's a beautiful piece of engineering.
But the document details what happens if the microprocessor controlling this intricate dance experiences a timing slip. Like if there's a microsecond delay in the task execution, that perfect 180-degree offset begins to slide.
And if it slides all the way to a 0-degree offset, you lose all that destructive interference.
And replace it with constructive interference.
Exactly. The ripples from motor A and motor B arrive at the capacitor at the exact same millisecond.
Which instantly doubles the ripple amplitude.
It does. And because heat generated by electrical resistance is calculated by the square of the current.
Wait, the square of the current?
Yeah, so doubling that ripple current doesn't just double the heat.
Oh, wow. It quadruples it.
Right. A software timing glitch physically bakes the capacitor from the inside out in a matter of seconds. The thermal load just completely overwhelms the component's ability to dissipate heat,
leading to rapid melting of the internal film.
Yep. Which brings us to the third mechanism.
Right, because we've talked about high-frequency ripples, but this one introduces a completely different threat, the second harmonic ripple caused by motor imbalance.
So in an ideal world, the three phases of alternating current running into a motor are perfectly balanced and symmetrical.
Which means they sum to zero on the DC side of the inverter.
In theory, yes, but physical reality is never perfect.
Right, there's always friction or whatever.
Exactly. A minor short circuit in the motor's stator windings, or slight unevenness in the mechanical bearings, or simply a temperature sensor drifting out of calibration.
All of that can cause those three AC phases to become asymmetrical.
Yes. And that physical imbalance feeds a massive low-frequency electrical ripple back into the DC link.
We're talking about frequencies in the range of like 100 to 500 hertz.
And this is where the physics of the capacitor actually work against us. The key concept here is capacitive reactance.
Which is a capacitor's resistance to alternating current.
Right. And the formula dictates that reactance is inversely proportional to frequency.
Okay, let me make sure I follow. So a capacitor can easily absorb high-frequency turbulence at 10,000 hertz.
Yes, its reactance there is incredibly low.
But when a heavy, slow 100 hertz ripple hits it, the capacitor's reactance is massive.
It acts like a brick wall. Pushing that low-frequency energy against that high reactance results in massive, highly destructive voltage spikes across the DC bus.
Okay, so the component is being attacked by high-frequency constructive interference, low-frequency motor imbalances, and its own chemical decay.
It's a miracle it survives at all.
Seriously. But there's a fourth and final root cause that adds brutal mechanical reality to the mix. Terminal loosening.
Right. These high-voltage connections aren't soldered onto delicate circuit boards. They are heavily bolted metal joints carrying hundreds of amps.
And those bolted joints are subjected to constant aggressive road vibration. I mean, you're driving over potholes, rough highways.
And over time, that vibration can cause the bolts to lose a microscopic amount of their axial preload.
The bolt relaxes, just a fraction of a millimeter.
But when that happens, the contact impedance, the physical resistance between the two pieces of metal, it jumps from microohms up to milliohms.
Now, a milliohm sounds entirely insignificant to me.
It does, but we have to apply the Joule heating principle we mentioned earlier. When you push 200 amps of high-frequency ripple current through even a few extra milliohms of resistance,
you generate intense, highly localized heat directly at the connection point.
right. The copper terminals heat up like the coils of a toaster. And that heat conducts straight down the metal pins and directly into the heart of the capacitor.
Which melts the nearby plastic film, the insulating layers fuse together, and you trigger an avalanche failure.
Resulting in a complete catastrophic short circuit.
Man. This breakdown clarifies exactly why this specific fault is so dangerous. I mean, we're dealing with an overlapping matrix of thermal decay, software timing errors, magnetic imbalances, and physical road vibration.
Yep.
All of it conspiring to destroy a single plastic component.
And crucially, a driver will never feel any of this happening. You can't exactly put a mechanical gauge on the dashboard to track microscopic film vaporization.
Right. There's no check engine light for your plastic film is vaporizing.
Exactly. By the time a driver notices a physical symptom, the vehicle is already in a catastrophic state. So the control system requires a highly advanced diagnostic architecture to read the electrical pulse of the vehicle in real time.
It's essentially acting as its own physician.
It has to.
So let's transition into that diagnostic architecture, the nervous system of the car. How does the vehicle's brain actually monitor this invisible decay while barreling down the highway?
The specification outlines an intricate hardware and software pipeline, and it begins with the extraction circuit.
Right, the ECG of the car.
Yeah. Keep in mind, the vehicle operates on a massive 400 or 800 volt architecture. You cannot connect a sensitive microchip directly to that kind of voltage to measure ripples.
The chip would just vaporize instantly.
Exactly. So the engineers utilize precision resistor dividers to scale that lethal high voltage down to a completely safe, tiny analog signal hovering between -1 and +1 volt.
But an analog signal in an environment filled with massive magnetic fields and switching inverters, that's going to be incredibly noisy, right?
Extremely noisy, which is why they feed that tiny analog voltage into a 10 megahertz delta sigma modulator.
Wait, 10 megahertz?
Yeah, standard analog to digital converters might sample a signal a few thousand times a second. This modulator oversamples the voltage 10 million times a second.
10 million times a second. That is mind-boggling.
It is looking so closely at the signal that it can actually see the tiniest ripples of turbulence riding on top of the massive DC wave. And it converts that turbulence into a high-speed digital bit stream.
And that bit stream is then fired across a digital isolator.
Right. This is a critical safety barrier, usually an optical or magnetic gap. It allows pure digital data to cross into the main microcontroller unit, or MCU.
While physically blocking any high voltage from ever reaching the low-voltage brain of the car.
Exactly. It's a firewall. And once that data safely arrives in the MCU, the software applies a strict 500 hertz high-pass filter.
So the computer is instructed to ignore the massive, slow-moving main DC voltage and only pass through the high-frequency turbulence. It isolates the ripple.
Yes. And this isolated ripple is fed into what is arguably the most complex part of the system, the virtual real-time estimation algorithms.
The virtual mechanic. The specs mention recursively squares and extended Kalman filters. I mean, these aren't just reading data. They are inferring physical reality from electrical behavior.
Right. To understand how these algorithms work, you have to look at system identification theory. The algorithm cannot physically measure the capacitance or the resistance inside the sealed box.
Because it's locked away.
Right. But it knows exactly what the inverter is doing. It knows the exact timing and magnitude of the electrical stimulus it is applying to the system.
And thanks to our high-speed extraction circuit, it can see the exact voltage ripple response.
So it compares the stimulus to the response. The algorithm starts with a mathematical model of what a healthy capacitor should look like.
Okay.
It predicts what the voltage ripple should be based on the current motor demand. Then it measures the actual voltage ripple.
So it looks for the difference.
Exactly. It takes the error, the difference between its prediction and reality, and uses that error to recursively update its internal mathematical model of the capacitor's health.
So it's continuously refining its understanding of the physical wear and tear of the plastic film.
Calculating the exact capacitance and resistance dozens of times a second.
And the system has absolute thresholds for this, right?
Yeah.
Like if the algorithm detects that the estimated capacitance has dropped by 10% from its factory rating, or if the internal resistance has jumped by 100%, it flags a level 1 warning.
Yes. The system recognizes the component is rapidly aging and it intervenes to slow the decay. But there's also a level 2 fatal error threshold.
What triggers that?
If the extraction circuit detects that the real-time ripple amplitude has spiked over 10% of the nominal bus voltage, so for instance, a 40-volt high-frequency ripple on a 400-volt system,
Oh, wow.
and if it sustains that for just 20 milliseconds, the software declares an immediate critical emergency.
20 milliseconds is nothing.
Yeah.
Alongside those thresholds, the software is also guarding against that carrier desynchronization we discussed earlier, right?
Yeah. Right. It constantly monitors the internal processor clocks. If the timing between motor A and motor B drifts more than 15 degrees from that optimal 180-degree offset.
It executes an immediate hard reset of the timers to forcibly prevent the motors from syncing up and doubling the ripple current.
Because if they sync up, it's game over. Now, diagnosing the problem is only half the battle. The vehicle actually must act to preserve itself and the driver.
And the document details specific fallback tactics based on the severity of the fault. Like if the system triggers that level 1 warning, the capacitor is aging but not yet critical, right, it enters a self-preservation mode to reduce thermal stress.
And the first step is pretty obvious. It limits the motor torque to 30%, which significantly cuts down the total current flowing through the system.
So if you're the driver, a little turtle icon pops up on the dash, and the accelerator pedal suddenly feels incredibly heavy and unresponsive.
Exactly. But the second step the software takes is highly counterintuitive. It performs pulse width modulation, or PWM, frequency shifting.
It actually increases the switching frequency of the inverters from 10 kilohertz to 12 kilohertz. Which, I gotta say, why does making the hardware work faster reduce the stress?
It's a great question. It comes down to the amount of charge transferred per cycle. If you increase the switching frequency, the amount of time the switch is closed during each individual cycle decreases.
Okay, I see.
Therefore, the capacitor is forced to buffer a smaller, quote-unquote, bite of electrical charge during every single on-off pulse.
So you're taking smaller, faster sips instead of massive gulps.
Precisely. The overall power delivered might be similar, but spreading it across faster, smaller pulses drastically reduces the peak thermal load on the capacitor's internal structure.
Oh, that makes so much sense. And this combination of lower total torque and faster switching allows the vehicle to safely enter a limp home mode, usually capping speed around 40 kilometers per hour, just getting the driver off the highway safely.
Right. But the limp home mode is a luxury for a slowly degrading component. What happens if the system hits that level 2 fatal threshold?
Right. A 40-volt ripple spike is detected. The spec states the system must react in under 60 milliseconds.
60 milliseconds.
Yeah. And if the vehicle is traveling at highway speeds, with the motor spinning over 7,000 revolutions per minute, the software executes a tactic called stepwise active short circuit.
Which sounds terrifying.
Wait, let's unpack this. If the car detects a fatal ripple while going highway speeds, it intentionally short-circuits its own motors, just to keep the voltage from blowing up the capacitor.
Yes.
Yeah.
And to understand why a short circuit is the solution here, we have to look at the alternative. If the capacitor is failing, the standard reaction might be to just open all the switches and disconnect the battery.
Like unplugging it.
Right. But at highway speeds, those motors are spinning incredibly fast. They're acting as massive generators. If you disconnect the battery, the magnetic energy trapped in those spinning motors has nowhere to go.
Oh. So the motors will push that energy back into the DC link.
And the voltage will spike uncontrollably. It would instantly destroy the inverters, fry the computers, and potentially cause a high-voltage arc event inside the cabin structure.
Wow. That sounds terrifying but brilliant. So letting the voltage spike is catastrophic. The solution is to intentionally short-circuit the motor phases together.
Right. By closing the switches and shorting the motor to itself, the system traps the magnetic flux inside the motor's own inductance.
It turns the motor into its own electrical cage.
Exactly, bringing the voltage on the DC bus down to zero.
But doing that instantly at 7,000 RPM, wouldn't that create a massive mechanical problem, like throwing a stick in the spokes of a bicycle?
It absolutely would. If you instantly short all three phases of a rapidly spinning motor, the magnetic braking force is so violent it could physically shatter the rotor, snap the axles, or lock the wheels and throw the car into a spin.
Which is why the tactic is stepwise.
Yes. The software doesn't slam all three phases closed at once. It shorts two of the phases together first.
Which bleeds off the initial spike of magnetic energy over roughly 1.5 milliseconds, kind of cushioning the mechanical blow.
And only after that initial energy is absorbed does it short the third phase, safely clamping the voltage under the safe limit of 720 volts without mechanically destroying the drivetrain.
It's an incredibly violent but perfectly orchestrated maneuver happening in fractions of a second. And the driver likely only feels a sudden, heavy deceleration.
Now, if the vehicle is traveling slowly, under 2,000 RPM, the kinetic energy in the motors just isn't high enough to cause that lethal voltage spike.
So in that scenario, the system simply executes a freewheeling command. It opens all the switches and lets the car safely coast to a stop.
The situational awareness built into the diagnostic code is staggering. I mean, it assesses the electrical decay, calculates the physical speed of the vehicle, and chooses a fallback tactic that balances electrical safety against mechanical stability.
Okay, so while this software is brilliant at catching the car as it falls, engineering a system that relies entirely on software intervention is a dangerous game. Which leads us into the physical architecture, the blueprint.
Right, the DFMEA, or Design Failure Mode and Effects Analysis.
Exactly. How do the engineers manipulate the physical world to ensure the software rarely has to step in?
Well, the physical foundation must be radically over-engineered. The specifications dictate stringent requirements for the capacitor itself. They don't just ask for a component that meets the expected electrical load.
No, they mandate a baseline 30% design margin for total capacitance.
30% is a huge safety net. Furthermore, the component must be rated to comfortably handle 1.3 times the absolute maximum current the inverters can physically produce.
They are essentially building a much larger thermal and electrical sponge, so it takes significantly longer for the system to dry it out.
That's a good way to put it. The spec also demands the baseline equivalent series resistance must remain under half a milliohm, even when the ambient temperature is baking at 105 degrees Celsius.
But upgrading the capacitor is really only addressing the victim of the stress.
Right.
The physical design of the surrounding architecture focuses on eliminating the stress at its source, and the primary weapon in that fight is the laminated bus bar.
The bus bar is basically the heavy metal highway carrying the high voltage direct current from the battery to the inverters.
Right. Traditionally, you might envision two thick, separate cables, one positive, one negative.
But this spec mandates lamination. The positive and negative copper plates are manufactured flat, wide, and sandwiched incredibly close together.
Separated by a specialized insulating layer that is less than half a millimeter thick.
Right.
Now I have to push back here. So by squishing these high voltage plates half a millimeter apart, they actually make the system safer by altering the physical magnetic field. That's incredible.
It is incredible. It's about manipulating stray inductance.
Okay, break that down for us.
Inductance is essentially electrical inertia. When the inverters switch massive currents on and off thousands of times a second, that change in current creates a rapidly expanding and collapsing magnetic field around the conductors.
And this magnetic field naturally resists the change in current.
Yes, and that resistance manifests physically as high-frequency voltage spikes.
Those are the exact voltage spikes that slowly destroy the plastic film inside the capacitor.
Exactly. Inductance is the physical mechanism generating the poison. But physics also provides a solution.
Okay.
When current flows out along the positive plate, it generates a magnetic field with a specific orientation. When it flows back along the negative plate, it generates a magnetic field with the exact opposite orientation.
Oh, I see where this is going.
Right. If you bring those two plates incredibly close together, less than half a millimeter, those opposing magnetic fields physically overlap and almost perfectly cancel each other out.
So the specification demands that this physical proximity must push the stray inductance of the entire bus bar below 15 nanohenries.
Aiming for an ideal target of 10 nanohenries.
By structurally choking out the inductance through magnetic cancellation, you eliminate the overvoltage spikes before they can ever reach the capacitor.
You're using the fundamental laws of physics to solve an electrical engineering problem rather than just throwing bigger components at the issue. It's synergy.
That is such an elegant solution. And the engineers apply that same philosophy to the software architecture. We touched on the 180-degree phase shift earlier as a potential failure point if the clocks desynchronize.
Right.
But the design documents reveal that this offset isn't just a dynamic variable. It is heavily hard-coded into the lowest levels of the base software.
The system is structurally forced to fire motor A and motor B in alternating beats,
which guarantees that constant state of destructive interference we mentioned. This hard-coded rhythm physically cancels out up to 40% of the high-frequency ripple current before it ever hits the capacitor.
And to handle the low-frequency second harmonic ripples, the ones caused by mechanical imbalances in the motor, the design implements adaptive notch filters.
Tell me about notch filters.
A notch filter operates on the principle of active noise cancellation, but for electrical circuits. It's a highly targeted algorithm that constantly monitors the current control loop.
Actively hunting for one specific frequency signature.
Right. In this case, the exact second harmonic of the motor's rotational speed. When it detects that specific low-frequency perturbation, it injects an inverse signal to delete it.
Preventing that low-frequency energy from echoing back into the DC link and hitting the capacitor's high-reactance brick wall.
The blueprint is undeniably a masterpiece. The capacitor is massively over-spec, the magnetic fields are neutralizing each other across half-millimeter gaps, the software is physically halving the ripple current, and active filters are hunting down the low-frequency anomalies.
However, a flawless blueprint is entirely meaningless if the manufacturing facility fails to execute it perfectly. Which transitions us from the design phase to the factory floor, the PFMEA, or process failure mode and effects analysis. Right. The manufacturing controls required to prevent the mechanical failures we discussed in the root cause analysis, specifically the terminal loosening and contact resistance.
Because we established that a minuscule increase in contact resistance creates localized Joule heating that will eventually melt the capacitor.
Therefore, the factory must guarantee microscopic perfection at every connection point. The specifications strictly prohibit soldering for the high-voltage pins.
They mandate automated laser welding to fuse the capacitor pins directly to the laminated bus bars.
But the document acknowledges that laser welding is not foolproof. I mean, a weld might look perfectly solid on the outside while hiding a microscopic air bubble or void deep inside the fused metal.
To prevent this, the factory process demands that 100% of the welded units undergo 3D automated X-ray inspection, or AXI, or high-resolution ultrasound scanning right there on the assembly line. The robotic scanners are basically peering through the solid copper looking for empty space, and the quality tolerances are absolutely punishing.
The total volume of void space across the entire weld must be strictly under 5%.
Furthermore, no single isolated air bubble can exceed 1% of the total weld area.
I'm imagining going to the dentist, but for car parts. Is a 2% microscopic air bubble in a weld really going to cause this massive vehicle to fail on the highway?
If we think about the physics we discussed earlier, the reason for the strictness becomes clear.
Okay.
That tiny void, that 2% air bubble inside a weld, it isn't just an empty void, it is a physical bottleneck for the electrical current.
Oh.
When you force hundreds of amps of high frequency ripple through that bottleneck, the current crowds together. That crowding creates microresistance, which generates intense concentrated heat.
Because the bottleneck is so small, the thermal density is extreme. That heat conducts straight down into the plastic film of the capacitor.
Exactly. A microscopic bubble of air essentially acts as a slow-burning thermal fuse that will eventually destroy the car's power system on the highway.
Man. So if the X-ray system detects a void that exceeds that 1% threshold, the assembly line software automatically engages a physical interlock,
rejecting the part and locking it off the line so human error cannot accidentally move it forward.
Macro-level safety is entirely dependent on micro-level manufacturing precision. Now, while the critical joints are laser welded, there are still components in the high-voltage path that must be bolted together. And we already discussed how road vibration causes bolts to relax and lose preload.
The manufacturing specification attacks this by completely banning human workers from using manual wrenches on the DC link assembly.
Wow.
Pneumatic impact tools are also strictly prohibited. The factory is mandated to use robotic, servo-driven screwdrivers equipped with closed-loop torque angle monitoring.
Okay, explain torque angle for a second. Standard torque wrenches just measure how hard you're twisting, right?
Right. But a torque angle system measures the twisting force, and it also measures exactly how many degrees the bolt continues to turn while experiencing that resistance.
Oh, I see.
By correlating the rotational angle with the torque resistance, the robotic system guarantees that the metal of the bolt is stretched to its exact elastic yield point,
Which ensures the maximum possible permanent axial preload is achieved, mathematically preventing road vibration from ever backing that bolt out.
But securing the bolt tightly is only half the battle. The electrical contact between the bolted surfaces must also be perfect.
So the assembly line uses optical character recognition cameras to physically inspect every single high-voltage bolt before the robot inserts it.
The cameras are verifying that the bolts have been treated with a highly specific phosphate coating. The engineering data proves that this specific chemical coating guarantees the physical contact resistance of the bolted joint will remain permanently under 5 milliohms.
Regardless of environmental degradation. If the camera does not detect the correct coating signature, the bolt is instantly rejected.
The level of automated paranoia on the factory floor is just astounding.
It really is. And there is one final manufacturing step detailed in the spec before the unit is allowed to leave the facility. End of line, or EOL, calibration.
Once the entire power control subsystem is fully assembled, but before it is ever mated to a real vehicle battery, a highly specialized testing machine plugs into the unit.
The environmental chamber exposes the system to extreme temperature variations, while the machine injects a perfectly clean, mathematically precise high voltage into the extraction circuit.
They are essentially running a baseline diagnostic on the car's sensory nervous system.
Exactly. Because even with the highest quality components, every single analog to digital converter and precision resistor will have microscopic manufacturing variances.
They'll drift slightly depending on the temperature.
Right. By injecting a known perfect voltage at varying temperatures, the testing machine can measure exactly how much the specific sensors on that specific car are drifting.
And it calculates the exact mathematical calibration offsets required to correct those microscopic errors.
The machine then permanently burns those specific offsets into the vehicle's permanent memory chip, the EEPROM.
This means the virtual mechanic algorithms we discussed, the Kalman filters tracking the degradation of the capacitor, they aren't using generic, assumed mathematical models.
They're using highly customized math, perfectly calibrated to the microscopic quirks of the actual hardware they are monitoring.
Which drastically reduces the chance of a false positive emergency out on the road.
We've dissected the microscopic physics of the failure, explored the software algorithms that monitor the decay, analyzed the physical blueprints designed to neutralize the electrical stress, and walked through the automated, laser-guided paranoia of the assembly line.
The system has been designed and built as perfectly as physically possible.
Which brings us to the final phase, the torture chamber, the Design Verification Plan and Report, or DVP&R.
This is the crucible. Before a single production unit is ever allowed to be sold to a consumer, pre-production units must survive a gauntlet of brutal physical destruction testing.
To mathematically prove that all those design and manufacturing controls actually work in the real world.
Right. The specification outlines 3 primary torture tests. The first is a purely thermal and electrical endurance test, the high-temp ribble cooker.
They take the fully assembled PCS unit, place it inside an environmental testing oven, and raise the ambient temperature to a blistering 105 degrees Celsius.
Once the unit is thoroughly soaked in that extreme heat, the engineers pump 120 amps of pure, unadulterated high-frequency ripple current directly into the DC link.
And they hold it there, continuously, for 1,000 hours straight.
That is over 40 days of continuous extreme heat and severe electrical turbulence.
To pass this test, the internal temperature of the capacitor cannot rise more than 15 Kelvin from its own self-heating.
And after the 1,000 hours are up, the total measured capacitance cannot have dropped by more than 3%.
Finally, they physically cut the sealed unit open and perform a microscopic autopsy. If there is a single millimeter of melted plastic film or any sign of metal layer separation, the entire design fails validation.
It is the ultimate proof of the 30% design margin and the self-healing parameters. If the engineers miscalculated the thermal dissipation or the ESR degradation curve, the 1,000-hour test will ruthlessly expose it.
The second test shifts from electrical endurance to pure mechanical brutality, the shake and bake. The unit is mounted to an industrial multi-axis shaker table.
The table violently shakes the entire assembly in all 3 spatial directions simultaneously, applying a constant acceleration of 35 meters per second squared.
That is essentially subjecting the unit to a constant randomized earthquake, generating over 3 Gs of vibrational force.
And while it's being violently shaken, the surrounding environmental chamber is wildly swinging a temperature from negative 40 degrees Celsius all the way up to 125 degrees Celsius.
And they run this combined thermal-mechanical shock test for 300 continuous hours.
This test is explicitly designed to challenge the robotic torque angle bolts and the laser-welded joints.
Throughout the entire 300-hour earthquake, sensors continuously monitor the electrical resistance of the high-voltage joints. To achieve a passing grade, the resistance cannot increase by more than 1.2 milliohms.
That specific metric mathematically proves that the extreme thermal expansion and contraction, combined with violent vibration, failed to break the permanent axial preload of the bolts.
Furthermore, the diagnostic system monitors the continuity of the circuit. Over those 300 hours, there cannot be a single electrical micro-interruption that lasts longer than one single microsecond.
They are vibrating a massive block of metal at 3 Gs and demanding that the electrical connection doesn't break for even 1/millionth of a second.
But as extreme as that is, the third test is where the validation process pushes into the realm of science fiction, the matrix.
Right. They aren't just testing the physical hardware anymore. They are testing the software's ability to react to a sudden catastrophe.
The spec refers to this as hardware in the loop, or HIL, fault injection. They take the actual physical computer, the vehicle's brain, and wire it directly into a massive FPGA supercomputer.
The supercomputer is running a flawless, real-time digital twin of the dual-motor drivetrain.
It simulates a scenario where the driver has the accelerator pinned to the floor and the virtual motors are screaming along at 12,000 RPM under maximum load.
The physical car computer is reading the data and believes it is hurtling down the highway at top speed.
While the computer is managing this extreme virtual load, the test engineers trigger a fault injection card. With a single keystroke, they instantly delete 50% of the virtual capacitor's health.
They simulate a massive instantaneous spike in the equivalent series resistance.
Here's where it gets really interesting. They aren't just testing the metal, they're plugging the car's brain into the matrix to see if it flinches when a virtual bomb goes off.
Exactly. And the passing criteria for this digital execution are incredibly narrow. We discussed the 60 millisecond reaction threshold earlier. When that virtual bomb goes off, the physical car brain must immediately recognize the corrupted data stream, realize the capacitor is theoretically melting, and command the stepwise active short-circuit sequence.
It must trap the magnetic flux and clamp the voltage under 720 volts, all within 60 milliseconds.
But the true test of the software's elegance is the mechanical constraint. The software must execute that stepwise short-circuit without physically ripping the virtual permanent magnets out of the rotor.
The specification demands that the torque shock, the violent mechanical braking force generated by short-circuiting a motor spinning at 12,000 RPM, must be strictly limited to under 5 Newton meters of force.
Because if the software panics and closes all the switches at exactly the same time, the torque shock would register in the thousands of Newton meters.
Simulating a shattered axle.
Right. By staging the short circuit over those precise 1.5 millisecond intervals, the algorithm bleeds off the lethal electrical energy while keeping the mechanical violence under that 5 Newton meter limit.
The brain successfully saves the virtual capacitor without destroying the virtual motor.
It is a stunning validation of the entire safety architecture, proving that the hardware and software can seamlessly coordinate to survive a worst-case scenario.
When you pull back and look at the entire journey, it fundamentally changes how you view the machines sitting in your driveway. I mean, we started deep inside a microscopic layer of plastic, watching how heat and electrical turbulence cause it to slowly eat itself alive. We traced the 10 megahertz digital pulse, monitoring at decay, unpack the physics of laminated magnetic cancellation, walk the factory floor where lasers and robotic sensors enforce microscopic perfection, and finally survive the brutal thermal ovens and digital matrix simulations required to prove the vehicle is safe.
This deep dive provides an incredibly clear picture of the current state of the art in functional safety. Because the physical world is messy, chaotic, and degrades over time, we currently rely on massive physical over-engineering, hypersensitive real-time diagnostic loops, and brutal physical torture chambers to guarantee safety.
It is an incredible defense mechanism against the chaos of reality.
But analyzing this level of integration raises a fascinating question about the future of engineering. I mean, the line between the physical hardware and the digital diagnostic twin is already blurring. As we move toward deeply integrated artificial intelligence and even more advanced predictive digital models, will these physical torture chambers and 1,000-hour oven tests eventually become obsolete?
Wait, really? Will the systems become so predictive that physical testing is no longer necessary?
Well, imagine an architecture where the vehicle's onboard AI is so deeply connected to the fundamental metallurgical and electrical physics of its own components that it doesn't even need to react to a failure.
Like it just knows.
What if the AI can perfectly simulate and predict the exact day its own DC-link capacitor will fail, decades before the raw materials are even mined from the Earth?
Wow. Moving from a system that brilliantly reacts to chaos to a system that completely calculates the future before it happens.
Exactly.
That is a heavy thought to leave on. Thank you for joining us on this incredible deep dive through the hidden architecture of electric vehicle safety.